Oh, okay. Hi, I'm George Mendoza from Baguio City, and this is the 13th episode of the Philippine Ruby Group podcast. Today I'll be covering the article Understanding the Enigma Machine with 30 Lines of Ruby, star of the 2014 film Imitation Game. So I just wanted to do that star. Okay, yeah. Anyway, the article was written by Albert Still last month on February 23 at redbadger.com. I'll share the link to this article in the show notes. Okay. My goal for this podcast is to try and explain the article, go deeper into it, analyze how the Ruby code, how the program with 30 lines of Ruby simulates the Enigma machine. Um, Reading that code made me understand uh, how the Enigma machine works internally. Although I don't have an although I have a very limited idea of how the Enigma machine is actually physically set up to encrypt and decrypt data. Uh, so just just a brief background on this topic. Uh, the Enigma machine was a machine that was used by the Germans in World War II to encrypt and decrypt messages. So it's like a typewriter wherein each character you type, each when you type on its keyboard, it lights up corresponding uh, bulbs on the machine, and each bulb represents uh, a character, the encrypted version of the key that you pressed. Hmm. In the imitation game, uh, Alan Turing uh, led a team of scientists, programmers to make a machine that cracked the Enigma machine's code. So because of because of their efforts, uh, they were able to decrypt the messages that the Germans were sending. So I haven't watched the movie yet, and my history is also not as well researched. So what I do recommend if you're watching this video, I recommend that you check out the blog article first. Um, read read the blog article and watch the embedded YouTube video in that article. The title of that embedded video is "The Inner Workings of an Enigma Machine." So that in that video, a lecturer demonstrates the Enigma machine and shows how it actually works. He shows the parts of the machine, and basically what I'll do with this podcast is just follow on that and try to explain and try to fill the uh, missing pieces that would hopefully get you to understand the machine a bit more. I'll also be I'll also be relying on another article uh, just as a way to provide some background on ciphers, and because these are the principles behind the machine. So the article is on Enigma and a method for its decryption. I'll also share the link later on. I haven't read this article uh, through. Actually, I just the first two sections were the only ones that I read because they already gave me idea of how of the principles behind the machine, the Enigma machine. So anyway, let me share that article right now. Here, here it is. So this is the article. Okay. What the Enigma machine uses two principles. What I've learned from this article is that the machine relies on two cipher encryption principles or schemes. The first one is that the machine is it uses a polyalphabetic scheme to change its encryption with each letter. So that if you've watched the video, you've seen that you've seen that case where he types the same letter on the machine and it produces different characters. So that's what I mentioned with polyalphabetic scheme. The second principle is that the machine employs asymmetrical encryption. By that I mean you use the same encryption you use the same cipher to encrypt and decrypt the data, your message. So this allowed operators to use one machine for both encrypting and decrypting messages, which would have been more convenient than having two machines separate for encrypting and decrypting. So I'll start with this article and explain how the polyalphabetic scheme works. So as mentioned here, the machine is based pretty much on the Caesar cipher. So this is a monoalphabetic substitution, which means that you substitute one letter for another letter. An example here is that you can substitute a letter with its nth neighbor in the alphabet. So for example, if you have the letters A, B, C, D, and F, if you can substitute its the n+2 neighbor of each letter for each letter. So A becomes C, B becomes D, C becomes E, and so on. So in this example, if you have the word deaf, it becomes your D becomes F, your E becomes G, your A C, and F H. So you have FGCH. So that's your encrypted message. So as mentioned by this article, the code is easy to break. Now, Arthur Scherbius, sorry for mangling his name. He's the one who invented the Enigma machine back in 1918. he came up with a better idea, which is to use a polyalphabetic scheme. So what happens with this scheme is that every time you encode a letter, the the encryption changes. And how that changes in this case is that your the your n increases. So example here is let's go back to that A B C D E F C D E F cipher. So the C D E F cipher will be used to encode the first letter. With the second letter, you shift one letter forward. So now your cipher is now DEFG. And for the third letter, you shift another letter forward. So now your cipher is EFGH, and then FGHI, and so on. So with his example, if you have the word def, it becomes, your D becomes F, your E, H, your K, sorry, your A, E, and finally your F, K. So that's why the encrypted message becomes FHEK. So this makes it a bit harder to this makes it harder to decrypt or to crack unencrypted message. As we'll see later, the Enigma machine's rotors, 3 rotors, implements this polyalphabetic scheme. So that's one big part of the machine. Okay, polyalphabetic scheme. The next part of the machine is what I mentioned earlier, the symmetric encryption part. So the idea is that you use the same cipher for both encryption and decryption. With the monoalphabetic scheme, this is actually not that hard to implement. So let's try that. I'm going to share my screen again. Okay, it's working. So let's say you have same letters A, B, C, D, E, F, G, and you want to encrypt the word def, but the cipher that you want to use, you want to make it possible to use the cipher to both encrypt and decrypt the message. One way we can do that is to assign each letter to its reverse in the alphabet. So Z, you have Z, X, Y, W, V, U, U, V, W, X, Y, Z. EUV, okay? So with this cipher, if we're going to encrypt the word def, we'd have D becomes W, E becomes V, A becomes Z, and F becomes U. Now, if we have this encrypted message and we want to decrypt it back to def using the same cipher, we can do that simply by setting the same characters to its reverse. TUV WXYZ. So T becomes GHFD CBA. To double check, your W becomes D, your V becomes E, your Z becomes A, and your U becomes F. So here we're using the same cipher to encrypt and decrypt messages. Nothing fancy, it's very basic. It's a bit fascinating. It's a bit fascinating to see this implemented though when you have in a polyalphabetic scheme. And that was the part that made me wonder, how does the machine actually work? How does it use a polyalphabetic scheme to that was at the same time generated symmetric ciphers? In, in order to figure that out, what I did is I traced the program that Albert Still wrote in the main in the article, and basically figured out, followed the code to see. I followed the code to compare both how it encrypts a letter and how it decrypts it. Okay, so now that we have gone to the background of the polyalphabetic scheme and the symmetric encryption, we can now go to the program. What I'm going to do is walk through the major loop of the program and run it, trace it, so that we can see how it implements this actual encryption. Okay, but first let's try to run the program and just check if it works. Okay, there's our screen. We're going to clear this. Okay, going to run the machine. Okay. Try to run that again without the tracing for now. Okay, let's run it again. The program takes an input string. In this case, it takes the message, I have taken more out of alcohol than alcohol has taken out of me. It encrypts it. So you have this RELL, etc. message. Then we're using the same algorithm to pass this message and decrypt it back to the original message. The program checks the decrypted message and compares it with the original message, and that's why it says here success. So let's go briefly at how the code looks like for this program. Okay, so here's the program by Albert Still. I've made some changes to the program. First off, I've seeded the random number generator so that it doesn't change. The encrypted message doesn't change. Makes it easier to trace. In its main loop, this big block here, what I did is store each character as it's processed by the machine. As you'll see later, what happens is that the character changes from uh, basically it's passed from one part of a machine to another, and as it's passed, it changes the character to something else. This is like if you're going through a hallway, and this is a bad metaphor, but you're going through a hallway and you see two doors and you choose one, and then there's another hallway, and then there's another two doors and you choose another one. So in a way, your character here passes through multiple doors. It changes paths until it reaches the point, the final door, which represents the character that is encrypted. So that's a really bad metaphor. Sorry about that. But anyway, if you watch the video, and I recommend that you do watch it before we go over here, you'll know that the Enigma machine, is composed of three main parts. You have the plug board, you have the rotors, the three rotors, and you have the reflector. So these parts effectively process the character that you enter and return its encrypted version. How does that happen? I think I'll need to demonstrate that with a diagram. Okay. Okay. So here's ASCII flow. Oops, I got confused there a bit. Let's clear this for a moment. Okay. As mentioned in the article, the Enigma machine functions like a circuit. So if you remember from your high school days or probably elementary days, your circuit is it's like a closed loop. You have, on one end, you have a switch. Right, let's type that, switch. And on the other end, you have a light bulb. And then somewhere in between, you have a battery that powers the circuit. What happens is when you press a switch, the light bulb turns up. And once you release the switch, the light bulb turns off. The Enigma machine assigns a circuit for each key in its keyboard. So for example, your switch, let's try and erase this. Your switch is now, for example, your letter I key. And when you press that letter I, it lights up the letter R. The letter R light bulb on the machine. This means that at any given time, since you have 26 characters in the alphabet, that means there are, at any given time, 26 circuits on the machine. Make sense so far? Okay. So that's the first part. The next biggest part of the Enigma machine are the rotors, which I'll represent with blocks here. As you remember from the video, the rotors function like a clock. You have a fast-moving rotor, your first rotor. You have a medium rotating rotor, and you have a slow rotating motor. When the fastest rotor completes its rotation, it moves the medium rotor one step. And when the medium rotor rotates once, it moves the slow rotor one step. As mentioned, it's like a clock. Your first rotor is like your second's hand. Your medium rotor is like your minute's hand. And your third rotor is like your hour hand. As these rotors rotate, they, ch they change the encryption scheme of the circuit. So each rotor has 26 characters, or 26, yeah, they represent 26 characters. When the rotor rotates, it changes the assignment of one character to something else. And as a result, with each time you type on the Enigma's keyboard, it changes the encryption and changes the cipher of the circuit. So we'll see later how this this actually works once we trace the program and follow the changes that it does. Now, aside from these three motors, there are two other parts that are important. The first one is what's called the reflector. So let's erase this. The reflector is at the end part of the, it's connected after the third motor. So I'm just putting it here. Unfortunately, it doesn't look nice. And the other part is the plug board, which the circuit passes through. Let's see. At the start and at the end of the circuit. Now, it's important to realize that these two parts, the reflector and the plug board, they're the ones that implement the symmetrical part, the symmetrical aspect of the encryption. On the other hand, as mentioned, the rotors are the ones that implement the polyalphabetic scheme of the encryption. So what we're going to do now is try to figure out how these parts change the character that you enter from letter I, it changes to R. And we'll see later, and we'll compare how it once you enter R, it becomes letter I. Okay. So for now, what I'm going to do is, how do I copy this one? Is there a way to copy? I think so. Let's that's one thing I didn't figure out. Okay, I'm not sure how to copy, so what I'll do is just create another smaller circuit here. I'm hoping that it has enough space to demonstrate the reverse of the scheme. Sorry. So in this case, what we want to check is if your letter R could become letter I. Okay. Okay. Let's go back to the code. Okay. As mentioned, the machine changes the circuit with based on using three parts: the plug board, the reflector, and the rotors. So the idea is that if you have a character I, it passes first through the plug board and it's changed to another character. That character is passed to the rotor, which turns it into another character, and so on. That character gets passed to rotor 2, and the output of that gets passed to rotor 3. Then the output of rotor 3 is passed to the reflector. At this point, the paths becomes reversed. The circuit now goes from 3 to 2, then to 1, then finally to the back to the plug board. At this point, the last character is the one that's actually the encrypted version. Better way to illustrate this is if we run the trace for the program and try to run the program. Okay, same program as before, but this time if I run the code, it traces each character as they go through the plug board, the rotors, and the reflector. So if you notice, what we have here, each row represents one character. You'll see that the first letter for each row is the original message. So here you have I have taken more, etc. Then each row represents how the character changes through the machine until we generate the encrypted message, which you can see at the far right of these rows. So RELLPD, this is the encrypted message. At the bottom, we're using the same algorithm, this time to decrypt the message. So you have the same RELL encrypted message here at the left side of the screen. And then for each row, you change the letter until it becomes the decrypted version here. I have taken more, etc. What I'm going to do is copy the first two rows and paste them on the diagram. Okay. Copy this one. and the first two letters. Okay, so these are the substitutions that were made for the first letter of the original message and for the first letter of the encrypted message. You'll notice that the letter, how it's substituted and how it's transformed to its encrypted message is just the reverse of how it's decrypted back to its original letter. You have here IIKN, and its reverse, you can see here the same thing, IIKN. What I'll do now is pass this traced message to the diagram and see how it lines up. Here we go. Unfortunately, we don't have a good place to put the characters. That'd be nice if we can do that here. Let's try anyway. Let's see if I can here. That's the best we can do. Let's try and copy the okay, erase the, oops, sorry, don't want to erase the whole thing because I don't know how to undo this. Let's paste it on the left side. Okay. So our I becomes R. And our, oops, and our R becomes I. Just to recap again, this is our circuit. These three rows here are our rotors. This one here is our reflector. And these two bars here are our plug board. So what happens is that the I gets passed to the plug board. So this is your I path. And once the plug board switches the path to another I path here. Then that I wire gets passes through your first rotor, which connects it to some K wire here. The K wire is connected to your second motor, which now connects to an N wire here. And finally, the third motor connects the N wire to a J wire here. Your J wire is connected to some reflector, which connects it to an R wire. Then the R is connected to a K, Q, and D. Finally, the D passes through again the plug board, which is finally connected to the light bulb marked as R. So that's basically it for encrypting a message. Once these rotors rotate, they change the wires that are connected from here to here, actually from this path up to the end, which results in a different circuit. The thing that bothered me again is how does would would it be possible for the same circuit to generate to generate a cipher that is symmetrical to the original? So if we just pass this transformations to the second diagram, so we have D, Q, K, R, J, N, K, I, and then I. What you'll notice is that think of it as each. Right now, previously we were talking about the wires of the diagram. Now, think in terms of if those wires were the edges of some graph. Think now about the segments that connect those edges and their interlying and the holes that interlining points that connect those edges. If you check, for example, the plug board here, it has 2 points which mark the end of the R and the D. So that's the same at the top for the R and the D. And for the motors, this motor has the points I, K, D, Q, which represent the same thing above, I, K, D, Q. My point here is that, especially for the motors, the motor state is the same. It has the same set of letters passing through it, IKDQ, IKDQ. For the second motor, it's the same, QK and K, QK and K. And for the third motor, the points are also the same, KRJN, KRJN. This means that the motor shares the same state for both encrypting and decrypting messages. And the same applies for the plug boards. So here we have in our plug board a connection between some I point and another I point, which is the same one used here at the end. And that same and the same connection that's used for RD is the same one that's used to process DR. So the plug boards and the reflector have the same concept. You have a reflector connecting J and R, and that's the same reflector that's connecting J and R here. So that explains how the symmetry works. At least I'm sure I'm not explaining it very well. Again, it helps to watch the video to understand the parts again. And I do recommend that you try this diagram on your own so that you can see for yourself. Uh, when I look at this diagram, the biggest thing that still bothers me is that I'm aware that this R here and this R here are the light bulbs, and the I here and the R here are your switches or the keys of the machine. When I press on these ones, on the keys, they light up different. Light up different light bulbs on the machine, but they rely on the same state of the machine. I mean the plug boards, the the rotors and the reflectors do not move, but they are employed for the same to get the letter R for I and the letter I for R. I guess it's because of the way the plug boards and the rotors are designed. If, once you read the code, you see that these connections are symmetrical because they use the same. They connect two characters in the alphabet. So that applies for the reflectors and the plug boards. So that's for the diagram. I know it's been a bit hard to explain. What we'll do next week is go back to the code, and this time focus on the nitty-gritty of it. The program that Albert Still wrote simulates the Enigma machine by using hashes to represent the rotors, the reflectors, and the plug boards. I hope that once we walk through it, we'll be able to understand the machine a bit better, much better than I explained it here. So that's for next week. Thank you very much for staying with me for this past hour. I hope to see you again next week, or next week will be the Ruby conference. If we can't do it next week, then probably next week. So thank you very much. Have a good weekend.